our previous lecture that this was the Coulomb force, this was the electric field intensity at any point which have the position vector r, this was the electric potential, and we have seen that we can express electric field as negative gradient of the electric potential. Okay, now we have a charge here at this point. Definitely we will have electric field intensity at this point P. Now we are bringing one charge from the point A to the point B, and the position vector of the point A, let it is RA, the position vector of the point B, let it is RB. So what we are doing? We are taking a unit positive charge from the point A to the point B. Now we will see how much work we have to do to take a charge from the point A to the point B. So what is work done? Work done is the electric field at that point to take a positive charge from this A to the point B. So work done will be given by this. Okay. Why negative sign? Because we have already seen in the derivation of potential that we are doing work against the field. That is why we have put a negative sign. Okay. See, if we solve this, what we will get? Q by 4 pi epsilon naught r square into dr RA to RB. By solving this, we will get Q by 4 pi epsilon naught 1 by RA minus 1 by RB. See, the result is very interesting. What we get? Work done to bring a charge from the point A to the point B depends only on the position vector of RA of the point A and the position vector of the point B. We can take the charge through this path, we can take the charge through this path, we can take the charge through this path, but the path may vary, but the position vector of A and the point B will not change. That means the work done to bring a charge from the point A to the point B will depend only on the position vector of the points. It is independent of the path. So it is a very important concept that it is to take a charge from one point to another under electrostatic force is independent of the path. Now we are taking the charge from the point A after covering, again we are coming back at the point A. That means we are making a closed path. So when we are making a closed path, this is the initial position, this is the final position. So now I can replace RB by RA for a closed path. So what we will get? We will get the work done over a closed path will be is equal to Q by 4 pi epsilon naught 1 by RA minus 1 by RA means equal to 0. So what we get? Under electrostatic force, the work done over a closed path is equal to 0, and it is independent of the path when we are joining any two points. This is called, so electrostatic field is called conservative field, because we know for a conservative field, conservative force field. Conservative field is that which is independent, the work done by which is independent of the path joining any two points, and work done over a closed path is always 0. That force is called conservative force. As we get the same result for the electrostatic force, in this case we are calling that electrostatic force is a conservative force. Now here with this result we will apply divergence theorem. So for a conservative force we get work done over a closed path is equal to 0. This we get. Now we will apply Stokes theorem to get a result. What is Stokes theorem? Stokes theorem is that surface integration curl of A dot ds, that is equal to closed line integration A dot ds, because we know a closed line, if we consider a closed line, it is always enclose some surface. So we can convert from closed line integration to surface integration. Now see, if we apply Stokes theorem to this equation, what we will get? We will get surface integration curl of E dot ds, that is equal to 0, which imply that curl of E is equal to 0. That means for any conservative force field, curl of the vector is always 0. So by using curl, if an electric field is given, whether it is a conservative force or not, by checking through this equation, we can check whether it is a conservative force or not by taking its curl. If that is equal to 0, we will tell that that force is a conservative. If not is equal to 0, we will tell that it is not conservative. Next is electric flux we will discuss. What is the electric flux? Now we will discuss the topic electric flux. So what we get next here? In this series we get next as curl of E is equal to 0. Electrostatic force is a conservative force, so we get curl of E is equal to 0, which is independent of the path joining them and work done over the same result. They come from same result, is equal to 0. Okay. Now what is electric flux? We have a small surface ds. So this is the direction of this surface. This is the direction of electric field. The angle is theta. So what is the component of E that is coming through the surface normally through this area ds? We can write as E cos theta into ds. That is component of electric field passing normally through the surface area ds is E cos theta into ds. That is the flux coming through this surface. So what is the total flux coming through this surface? We can integrate over d phi, that is equal to E cos theta ds. Now see, it is like mod of A mod of B cos theta, that is equal to A dot B, which is given as E dot ds. So flux is given by E dot ds. So what is flux? Flux is defined as the electric lines of force passing normally through the surface, that is the electric flux. What is the number of lines of force passing normally through the surface? That is called the electric flux. So we get flux is equal to integration E dot ds. Now from using Coulomb's law, we will see what is the value of this flux and how this result will lead to Gauss's law in electrostatics. So phi is equal to, we are taking a sphere where we have taken a small surface area ds. This is ds. This is small surface area ds. So what is now if an electric field is coming towards this sphere, so what will be the flux? Phi is equal to E dot ds. That is equal to Q by 4 pi epsilon naught r square ds r cap into ds. This is the value of E, this is ds. Now see, the direction of ds and the normal component of electric field to the surface, they are in same direction. So that is cos 0 is 1. So we will get Q by 4 pi epsilon naught r square. Now if we take the integration of ds, that means we are taking the surface area of a sphere having the radius r. So what we will get? 4 pi r square. That is 4 pi r square. So calculating this 4 pi r square will cancel out. We will get Q by epsilon naught. So what do we get? The flux through any surface does not depend on the shape of the object. It depends on how much the charge enclosing by that sphere or that surface, that closed surface. So this result gives us Gauss's law in electrostatics. What it tells? It tells that the electric lines of force coming normally to the surface is equal to 1 by epsilon 0 times the charge enclosed by that surface. That charge is Q, which was enclosing by this sphere. This is the integral form of Gauss law in electrostatics. Now using divergence theorem, we will get the differential form of Gauss law. What is divergence theorem? I think all of you know that from your vector calculus knowledge. That is divergence V into dV, that is equal to closed surface integration A dot ds. See, here the form is E dot ds, which is equivalent to this. By applying divergence theorem to the left hand side, what we will get? We will get divergence of E into dV, that is equal to 1 by epsilon 0 times. Now we can replace Q. How we can replace Q in terms of volume integration? Let we have a volume V where the total charge is Q. So what will be the volume charge density in this case? Total charge divided by total volume. Now if we take a small volume element here, dV, by integrating this dV, we will get this whole V. So Q can we write as integration rho into dV, where rho is the volume charge density. By integrating this dV, we will get this V. So this thing I will replace here. This Q I will replace by integration rho into dV. So we will get divergence E minus rho by epsilon naught is equal to, into dV, that is equal to 0, which will lead to divergence of E is equal to rho by epsilon naught. This is the differential form of Gauss's law. So what we get? We get up to this. Then we get the differential form, which is given by rho by epsilon naught. That is divergence of E is equal to rho by epsilon naught. So let me clear the rest of the things except the integral and differential form. The integral form we get of Gauss law, EdS equal to 1 by epsilon 0 times the charge enclosed by the surface, and differential form is divergence of E is equal to rho by epsilon naught. This Gauss law is very useful in determining the electric field at any point inside a surface. Now there is a limitation. That surface should be symmetrical in shape. It may be either spherical, it may be either cylindrical, like it will be symmetry in shape. And another limitation of Gauss law is that as it is a dot product, we cannot find the direction of electric field at any point using the Gauss law. We can find its magnitude only. Okay? Okay. Now see, we know, see the list. In this list, we get one equation that electric field can be expressed as negative gradient of the potential. So if we can replace this E as minus gradient of V, that equal to rho by epsilon naught. Just multiply it, we will get Laplacian operator is equal to minus rho by epsilon naught. This is called the Poisson's equation. This gives a relation between potential and the charge density in any region. Now let in any region this charge density is equal to 0. It may happen that in any region you have some region where you have some potential but there is no charge in that region. Maybe the potential comes from the influence of the charges which are in outside this region. So let in this region rho is equal to 0. So definitely we will get grad square V is equal to 0. Remember one thing, that rho is equal to 0 in one region does not imply that V is also 0 in that region. This equation is called Laplace equation. This is the Laplace equation. So how we arrive at this equation? Starting from the definition of flux, we get integration E dot ds equal to q by epsilon naught. Then in this integral form of Gauss law, we apply divergence theorem while we get differential form of Gauss law. Then using the concept that electric field can be expressed as negative gradient of potential, we get Poisson's equation. Then if in any region rho is equal to 0, we will reduce to the Laplace equation. Now we will see some application of Gauss law and Laplace equation. Okay. As we had discussed in our last talk of electrostatics about the Gauss law, where we get the integral form as integration of E dot ds equal to 1 by epsilon naught times the charge enclosed by that surface. Today we will see its application. Application number 1 to solid sphere which is non-conducting, or we can write within bracket non-conducting sphere. Let we have a sphere of radius a which is carrying a total charge q. We have to find electric field at a distance r, where r less than a, r is equal to a, and r greater than a. In this three region, that means r less than a means inside the sphere, r is equal to a means on the surface of the sphere, r greater than a means outside the sphere. In this three region, using Gauss law, we will find the electric field intensity at that point. We are looking for this last one first. So r greater than a means it is a point P which is outside the sphere. So we can draw our Gaussian surface here of radius r. So what is the Gaussian law? Gauss's law tells that r E that we will find at r greater than a dot ds. What is the ds? ds is the surface area of the Gaussian surface. Now see, here my Gaussian surface is again a sphere having the radius r. So what is its total surface area? Definitely it is 4 pi r square into 4 pi r square, that is equal to 1 by epsilon 0 times I have to find the charge enclosed by this sphere. Now see, it is the q which is enclosed by this sphere, because this r radius is outside a, so the charge enclosed by this Gaussian sphere of radius r will be definitely this q, that is q. So E for r greater than a is 1 upon 4 pi epsilon naught q by r square. So it is inversely proportional to r square for r greater than a. Now we are on this point on the surface, that is when r is equal to a. See, at r is equal to a, the Gaussian surface and the original surface will coincide. So when it will coincide, the shape is also same. At that time, again the Gaussian sphere has the radius r or a, and it is enclosing the total charge will be this q again. So for E, r is equal to a dot 4 pi, this is outside, this is on, here I will take a point which is inside. 4 pi a square, that is equal to q by epsilon naught. So we will get E for r is equal to a q by 4 pi epsilon naught a square. So these two are clear for r greater than a and r less than a. It was rather easy. Now we will find the electric field at a point inside the sphere. So let us draw a circle. Let this point is now r, which is less than a, and we will draw a circle, that is Gaussian surface here, having the radius r. So now what I will get? Just I will here write down the results of r greater than a and r less than a equal to q by 4 pi epsilon naught 1 by r square, and r equal to a, it is q by 4 pi epsilon naught 1 by a square. Now we will find for r less than a. Now E r less than a, that we will find dot ds means again it is a Gaussian sphere of radius r, means 4 pi r square, that is equal to 1 by epsilon 0 times, let that charge, now it is enclosing, is q prime. Why q prime? Now q was the charge within a sphere of radius a and it was uniformly distributed, and so that the amount of charge now that is enclosing by a sphere of radius r will not be definitely equal to q. I have to take the percentage, what percentage of q is enclosing by a sphere of this radius r. How I can find that? As the charge is uniformly distributed, we can find the volume charge density. What will be the volume charge density? That volume charge density rho is equal to will be total charge divided by total volume 4/3 pi a cube, that is total volume of the sphere. Now what will be the charge enclosed by a sphere of radius r? That means charge, volume charge density multiplied by the volume of this sphere of radius r, that is 4/3 pi r cube. That is, now the fraction is r cube by a cube. So that is, this is actually q prime, this is actually q prime. So now I get the value of q prime, which is the amount of charge enclosed by a sphere of radius r. So I will replace this value of q prime, that is q is q r cube by a cube. So just simplify this, we will get E for r less than a, that is equal to q r by 4 pi epsilon naught a cube. This is the electric field at a point inside the sphere. Now if we want to draw a graph with r along x-axis and let the electric field along y-axis, so we see for r less than a, let this point as r is equal to a. So see, for r less than a, all the terms are constant except this r. So r less than a, electric field is directly proportional to r, and for r greater than a, electric field is directly proportional to 1 by r square. That means if I up to r is equal to a, they are directly proportional, and above r is equal to a, it is inversely proportional. So here E is inversely proportional to 1 by r square, and here it is E is directly proportional to r. This is the variation of the electric field with the distance for a uniformly distributed solid sphere that must be non-conducting of radius a. Why I am giving stress on this point non-conducting? Now we will come to this point. Okay. Now we have a solid sphere which is conducting. Now the same calculation we will do for a sphere which is now conducting. Q is the charge given to the sphere. Let Q is the charge given to this conducting sphere of radius a. Now we know if it is a conducting sphere, for a conductor the charge always resides on the surface of the conductor. So the charge will come only on the surface. There will be no charge inside the sphere. Okay. Now again we have to find electric field at r greater than a, r is equal to a, and r less than a. When we are considering r greater than a, let this point is r, which is obviously greater than a. So when we will apply here the Gauss law, like the previous problem of non-conducting, we will get the total charge enclosed by it will be q. So it will be q by 4 pi epsilon naught r square, same. And when we are on the surface, again it is enclosing the charge, this whole charge q, we will get q by 4 pi epsilon naught a square. Now we are considering a point E for r less than a. Now when we will go inside this conducting sphere and we draw a sphere of radius r, let this radius r. Now see, now this Gaussian surface of radius r is not enclosing any charge, because all the charges are outside this, on the surface of the sphere, or outside this sphere of radius r. There is no charge within this sphere of radius r. So as the charge enclosed by it is 0, definitely the electric field will also become, yes, 0, is equal to 0. So now if we want to draw here in this case the graph for radius r, and this is the electric field E. So up to r is equal to A, it is 0, and above this it will vary with 1 by r square. That is the, so we have seen 2 application of Gauss law. We will now do more, one for solid sphere non-conducting, one for solid sphere which is conducting. Or you, this problem you can take same as a hollow insulating sphere where Q is the charge distribution. The same answer will be same for that.